Hello students, my name is Malindra Easters and I am obviously a mathematics teacher. Today we are going to look at speed, distance, time questions, parity with numbers and then proportion questions. What are the quickest ways to solve problems in Maths Olympiads? So let's go have some fun.
The first questions that we are going to have a look at are the speed, distance, time questions that you normally get in your Maths Olympiads. So let's read through this. A train, 1 kilometer in length, is traveling at a constant speed of 20 kilometers per hour. At precisely 1 o'clock, the train enters a tunnel 1 kilometer long. At what time does the train leave the tunnel? Okay, so you will see that all the questions that we're going to go through with speed, distance, time, I always put the little formula for you on the side if you at all want to use it at any time. You can always refer back to this little beautiful magic triangle. So if you want distance, you will take the speed and you will times by the time. And if you want the speed, you will then take distance divided by time, etc., etc. So I normally call this the DSTV triangle. That's how I normally remember it. So you can do the same, and you will notice that it's basically the same triangle that you use in your normal maths curriculum as well. Okay, so to understand this problem, we kind of have to visualize what is going on here. So that is what I did for you here. And I'm going to move the train so that the train is at the start of the tunnel. So this is when we are going to start calculating the time. So we actually need to know how far is this train actually going to travel before, so that I can work out the time for that specific distance. And luckily I do have the speed of this train. So you can see that at the start, this is the front of the train, and this is when time will start, elapsing. So as the train is traveling through the tunnel, you can see that at 1 kilometers, this is the length of the train, and this is also the length of the tunnel. So at that stage, after 1 kilometer, the whole train will be inside the tunnel. And then the train will be leaving the tunnel, and please have a look at the start, well, at the front of the train. And as soon as the train leaves the tunnel, the start of the train, and this is the distance that we have traveled so far, is 2 kilometers. Okay, so that's what you need to understand. So keep your eye on the front of the train, and as you are moving towards or through the tunnel and to get out of the tunnel the other side, how far did the front of the train move? Okay, so we know that we are traveling at a speed of 20 kilometers per hour, and we do know that we need to travel for 2 kilometers. So I need to figure out what is the time that that's going to take me. So I used my little magic triangle for distance, speed, and time. I took the full amount of distance traveled, so that's 2 kilometers divided by the speed, and I then get an answer of 0,1 hours. Okay, remember, be careful. The units that you are working in will be the units of your answer. So you can see that that's kilometers per hour, so your hours will be given after that calculation. You then want to take that and times it by 60 to convert it to minutes. Okay, and that gives you 6 minutes. So that means it takes the train 6 minutes to travel for 2 kilometers. Okay, for that distance. Now, if the train entered the tunnel at 1 o'clock and it takes 6 minutes for the train to get through the tunnel and the other side out, you just need to add 6 minutes to your 1 hour. Okay, so that's why your answer is 13:06. Okay, that is when the train will leave the tunnel. Right, let's go to problem number 2. Fred cycles up a hill at a constant speed of 5 kilometers per hour. He cycles down the hill at a constant speed of 45 kilometers per hour. What is his average speed? Okay, so what you need to understand, if I want to work out average speed, it's always the total distance, so that's the total distance traveled over the total time that this journey took me. So again, I normally draw out my little scenarios for me so that I can see what is going on here. And as you can see, this is my hill, and we are assuming that it's the same distance up the hill than down the hill. So you will see that I made my total distance there x, because I actually don't know how far I am traveling. But I do know the speed up the hill is 5 kilometers per hour, and down the hill it's 45 kilometers per hour. And then you'll see that I worked out the time for each journey. And I know that the distance traveled up the hill is x. If I divide that by my speed, I get the time in terms of x. And the same for the time downhill. And now I need to work out the average speed. So that's, like we said, total distance divided by total time. And the total distance traveled is up the hill plus down the hill. So that's x plus x. Your total time is then your time up the hill plus your time down the hill. And you'll see that this is quite an ugly fraction to simplify. But if you keep your wits about you, it's not actually that bad. You just need to understand that you've got a fractions over fractions here. So what I did here was I took a lowest common denominator of 45. I then times my numerators with what is missing, basically getting both denominators to 45. And you can see my numerator, I just simplified that to 2x. Then you can also add 9x plus x to give you 10x. And this is going to be a little bit of a times and tip situation here. So this is 2x divided by this fraction. So you'll see that I took the division line and I changed it to a division sign just to make it easier for you to see what's happening here. And the rule says, if we divide with a fraction, the quickest way is to change the division sign to a multiplication and then swap the fraction after the sign. So we call it, a lot of teachers call it tip and times. I actually call it times and tip because that's the order in which this is happening. And then after that, you are just multiplying two fractions basically. If you want to convert this to a fraction, that's also fine. So that's 2x over 1 basically. And if you want to start cancelling, you can do that. If you want to multiply the top first and then get an answer, going from there, we can just times the tops. So you'll get 90x. And then you times the bottoms, the two denominators, 10x. The x's will cancel and you get your answer of 9 kilometers per hour. Then let's check out question B there. So it says there, if he is able to increase his speed down the hill, what is the maximum average speed that he will be able to achieve? So we know that this is our original expression that we had for the speed that we calculated. And you will see and notice that what I've done here is this is my speed down the hill. And I'm just adding another variable to that because if I'm increasing my speed, I'm going to add some kind of sum or value to 45. And what I want to try and do now with this fraction is to kind of manipulate it so that I can get, so that I can see if there's something that I can maybe move out or, and then it will become clear on what the maximum average speed is going to be. So you'll see from my calculations here, I did the same as what I did at the top. So I had to find an LCD between these two denominators, which then gives you 545 plus y. You then times each of these numerators with what is missing in the denominator. You'll see it looks quite ugly, but just stay with me. Then at this stage, okay, I didn't show my steps here, but this is I'm dividing by this massive fraction. So, you know, if you times this in, you're going to get x, 45x plus xy plus 5x all over 545 plus y. Okay, so all I did was times that x into the bracket, and then we are going to times and tip. Exactly like we did at the top. It just looks a little bit more complicated with all the x's and y's. And if you simplify this, you get 50x plus xy. So that's how I got to this answer here. If you just want to come down to my steps here, I said 2 times 5 is 10. I kept my x outside of the bracket, and at the bottom I have 50x plus xy. I then take out an x at the bottom as a highest common factor, so I'm just moving that out of those two terms, putting it in front of the bracket, and you'll see that now you've got one term. So although you've got brackets, remember that brackets combines, so you've got everything is multiplied at the top and everything is multiplied at the bottom. So if you've got one term over one term, you can start cancelling and the x's will cancel there. And you then end up with a fraction that looks like this. Okay, so this is where it tends to get a little bit tricky. So we have our fraction simplified. We have a 10 outside the bracket there for my numerator, 45 plus y in brackets, and then my denominator is 50 plus y. So what we want to do with this fraction is try and convert it to two fractions, so that if I have the two fractions and I simplify this and work backwards, I must get this answer again. So the numerators of my two fractions, if I add them all together and multiply everything out, I should get the same answer that I get here at the top. So let's quickly simplify this so that you can see what I'm saying. So if I take this 10 and I times it by 45, I'm going to get 450 there. And if I take the 10 and I times it by y, I'm going to get 10y. So you basically want an answer of 450 plus 10y. So I'm now going to split this into two fractions. You'll see that my denominator of 50 plus y for both of the fractions are the same, which it should be because, you know, if I'm going to work backwards, if my denominator is the same and I'm subtracting fractions or adding fractions, my denominator stays the same. Then my 10 that I had as my highest common factor or my number outside my bracket, that stays outside. Okay, and I'm going to write that over my first denominator of 50 plus y. But I'm also going to times that by 50 plus y because eventually I want these two to cancel. And you'll see in a moment why I need that to happen. Okay. Now let's see. If I do that, if I times 10 with 50, I get 500. And if I times 10 with y, I get plus 10y. Now remember, after I simplify these two fractions, I need to get the same answer as what I have here at the top, the 450 plus 10y. So you can see I'm getting 10y there. That's great because I needed 10y. But here I'm getting 500. Now that's a problem because I want 450 as an answer. So I can see by using inspection, okay, that's why I wrote it there. By using inspection, to get 450, I know that I need to subtract another 50 in my numerators for all of this to simplify back to what I originally had. So that is how I got to these two fractions and the two numerators. And now what happens is, exactly like I said previously, the 50 plus y cancels with this 50 plus y. And then you just have the 10 left. And after that, you will see that minus 50 over 50 plus y, that is then your fraction that you are subtracting with. So what is this answer? So we just worked out the speed, the maximum speed that this thing will ever reach. Now 10 will definitely have something to do with this, but let's first talk about this fraction. You can see that I said plus y there. Now we originally added a y variable to explain that we are increasing the speed by some kind of amount. We don't know how fast we are going, but we know we are going faster than usual. So, to explain this, I'm going to use an example. If I take 50 and I divide it by 1, my answer is going to stay 50. If I take 50 and I divide it by 2, my answer is going to be 25. If I take 50 and I divide it by, let's say, 10, my answer is going to be 5. So what I want you to see is as the denominator is getting bigger and bigger, the answer for the fraction is actually getting smaller and smaller and smaller. So if you increase this with a lot, like if you go as fast as you possibly can, you can increase it by quite a bit. That means that this whole fraction is going to tend to 0. It won't be exactly 0, but it will be very, very close to 0, which means that your maximum speed will actually never be 10, if you think about it, but it can become very close to 10. So your maximum speed can be close to 10, but it will never ever reach 10 kilometers per hour. So whatever increase you have with your speed, this fraction is going to get less and less and less. And that is how you basically get to the answer there. Okay, so I hope that made sense. Let's have a look at the next question. If John rides his bike to school and walks home, he needs 1.5 hours for the round trip. If he rides his bike both ways, he needs half an hour for the round trip. How much time would he need for the round trip if he walks both ways? Now, again, there's quite a lot of ways to solve this. You can use the magic triangle and go and find speeds and distance and times and set up equations, but there's a very quick way to do this, and that's just using logic. So if you look at my little diagram that I've drawn for you, this is the scenario that's playing itself out. So they said that if you just go by bike and you go to school with your bike and you go back home with your bike, the whole round trip takes you 30 minutes, which means if you take your bike, it's going to take you 15 minutes from home to school. So I just split that time in half. And then what they said, the next bit of information, is that they gave you the fact that if you go first bike and then you walk home, all of that is going to take you 90 minutes. They said 1.5 hours. But we know from the top scenario that if I'm going to take the bike, I know that this trip is going to take me 15 minutes. So all I need to figure out is what the time is going to be for me to walk home. Well, that's easy, because if I'm walking for 90 minutes, or if the whole round trip took me 90 minutes, and 15 minutes of that I used the bike, then I just subtract that from 90 to get to the amount of minutes that I walked. And this is if you are walking one way. So walking one way is going to give you 75 minutes. And then finally, if you draw another diagram, this is your final answer. How long is it going to take you to walk both ways? Well, you know that walking one way, whether you walk home or school, that's going to take you 75 minutes. And if you walk again, that's another 75 minutes. And if you add that and convert that to hours, you get your answer of 2.5 hours. Okay, so you don't have to do a lot of calculations. You just need to think about this logically, and then you can actually get to the answer quite quickly. Remember, in the Maths Olympiads, you want to try and save time. So if there's a quicker way to get to an answer, use it. 3 athletes run around a circular track having a circumference of 400 meters. They start at the same time from the same place, and they have 3 different speeds. How many rounds would they have run all together after 12 minutes? So again, lots of ways to solve this, but I'm going to use ratios. That is the quickest way to do this and to go about getting the answer. So I wrote down all 3 ratios of the first person, second person, and third person, and I converted all the hours to minutes, as my answer that they want is also in minutes, 12 minutes. Then I worked out how far will each of these people run in 12 minutes. So I took 60 and I times that by 12 over 60, which I did the same there. So if you've got a ratio, and you times or divide by a factor on both sides, you can actually simplify the fraction quite easily. So the 60 minutes, 6 kilometers and 60 minutes then simplifies to 6 over 5 kilometers for 12 minutes. And I did the same for each of these. So I converted all of them to 12 minutes. Reason for that is I want to see how far, if all of them run together, how far all of them will be running. So then I took all the distances, because all of them are now running for 12 minutes. So if I take all of their distances, so I take 6 over 5, 4 over 5, plus 2, if I add all of those kilometers together, you get 4 kilometers in 12 minutes. Awesome. So that means that they are running 4,000 meters. Okay, I don't have that there. Let's put that there. 4,000 meters altogether in 12 minutes. So they want to know how many rounds, would they run together if a round is 400 meters. So you take the total amount of meters that they all ran together and you divide it by 1 round. And that gives you 10 rounds altogether. That is, I think, the quickest way to get to it. There are other ways as well, but ratios are always a good bet to save time. Traveling at an average speed of 40 kilometers per hour, he will be 1 hour late to his destination. Traveling at an average speed of 60 kilometers per hour, he will be 1 hour early. At what average speed in kilometers per hour should we travel in order to arrive on time? So I drew up a little diagram for you, just to show you how this is looking in words. So you'll see here in the middle, that is when you are on time. And the 2 scenarios that are playing off here is if you are traveling at an average speed of 60 kilometers per hour, you are going to be 1 hour early. And if you are going slower, you are going to be 1 hour late. Now, what you want to do is write down an expression for the distance traveled to be on time. But you want to write it in 2 different ways, because remember, your 2 distances, if you want to be on time, is going to be exactly the same distance. So to explain that, I used a little equation here. So I said the distance early will equal to the distance late. Remember, whether you are early or whether you are late, you are going to travel the same distance to get to your destination. So the distance from the starting point can be calculated in 2 different ways. And remember, I'm using the magic little triangle here. So distance to get distance, you take your speed and you times it by your time. So I made my time to be on time. I made X. But if I travel at 60 kilometers per hour, I'm going to be 1 hour late. So my time there is going to be X minus 1, and this is my speed. And if I times them, I get the distance. Another way to explain the distance is to take the other scenario where I'm driving at 40 kilometers per hour and I'm then an hour late. So that's going to be X plus 1. Remember, X is the variable that I'm using to be on time, because I don't know how long that takes. And that's what I need to work out. So then you've got a beautiful equation that you can solve. You can multiply out your brackets, collect all your X terms on the left, take everything else to the right, and you get 5 hours. So 5 hours, it will take you 5 hours to be on time. And then we just need to quickly find out how far that is. If you look at the question here, at what average speed should we travel in order to arrive on time? So we need the speed, and speed is total distance divided by time. So we need to find the distance, and we have X now, so we can just plug that back into the original equation, one of them, and this was X minus 1. So that's when I drive 60 kilometers per hour. I know now that being on time is 5 hours, and that gives me a distance of 240 kilometers. So to get my speed, you take your distance and you divide it by your time. So your final answer for your speed there is 48 kilometers per hour. Very nice question. Water freezes at 0 Celsius and boils at 100 Celsius. On the SAMO scale, water freezes at 20 degrees and boils at 170 degrees. The two scales are linearly related. What is the temperature on the SAMO scale if it is 80 degrees on the Celsius scale? So the first thing that we need to understand is, what does this word mean? Linearly. Why? If they are linearly related, that means that the increase on your SAMO scale from the 1 degree to the other will be directly relatable, or directly proportional, if you want, to your increase on your normal Celsius scale. So to draw this out, I am going to use a table to explain this to you. So these are all the values that they gave to us. And you can see that on your SAMO scale, they gave us 20, 170, and they link up with 0 and 100 on the Celsius scale. And I made my SAMO my input values, and then my output values will be Y. So what you want to try and get to is to see, you want to compare the increases here, because the increases, if they are linearly related, will always be relatable in direct proportion. So if I, on the Celsius scale, increase by 100 degrees, that will be exactly the same on the SAMO scale, increasing by 150. So the 100 to the 150 increase is your relatable scale that you can use now. So if you look at this one, so if I am increasing by 80, you want to increase from 20 to X, you want to increase in the same ratio as what you've just done in the purple, from 100 to 150. So to do that, you can use ratios. You can see that I wrote down my increases. So I am relating 150 to 100, my increases for my SAMO to my increases for my Celsius meter. I want to find out what should be my increase for my SAMO. if my increase in my Celsius meter is 80. And because they are directly proportional, you can just cross multiply there to get an equation out. Or very easy, you can just work out, what are you timesing with both sides, what factor. But the easiest is just to cross multiply, and you then get 120. Okay, which means that is the increase that occurs. So that is going to be that increase. That is not the actual x answer. So just be careful there. I should have maybe used a different variable. So maybe let's make this z, okay, so that you don't get confused, because I'm looking at the increases. The increases are directly proportional. So the answer is what will this x be? What is the temperature on the SAMO scale if the increase from 20 to this is 120? Well, then you just add 20 to that, so your answer there is going to be 140 degrees. So that is the quickest way to do that. You can also use the straight line equation if you are in grade 9, if you learned your y equals mx plus c linear equation, or your patterns formulas, you can also use that, but this is definitely the quickest to get to this answer. Given two integers, a and b, consider the number ab times by a minus b. Can you determine if this is going to be even or odd? Now, to answer this question, there's a few rules that you need to know, and I'm going to share those with you before we even start working this out. And well, you don't really need to study this. It's very useful to know this because you can use this in calculations when it comes up in Maths Olympiads. But I also used examples to explain this to you. So it's not really necessary to study this, because you can also just use an example to quickly remind yourself of what happens here. So there's 6 rules when it comes to adding or subtracting even and odds, and multiplying with even and odds. The first one says that if you take 2 even numbers and you add or subtract them, you will always get an even. So there's your first example. 2 plus 2 is equal to 4. Then if you do the same with odd numbers, so if you add or subtract 2 odd numbers, you also get an even. And if you have 1 even and 1 odd, and you add or subtract them, you will then only get an odd answer. Then for multiplication, if you times 2 even numbers, you always get an even. If you times 1 even and 1 odd, you will always get an even. And then finally, if you times 2 odds, it will always give you an odd. So remind yourself of that, because then this example becomes quite easy. So this is what they want us to work out. And we need to go and check, what each of these scenarios will look like. How will the answers look like if A is even and if B is even, or if A is odd and B is odd, or if A is even and B is odd? So the first scenario that you will see that I had a look at here is I said if A and B are both even. So A is an even number and B is an even number. Now, because I'm timesing here, that's an even times an even, and we know that that must give us an even. We also know that if this is even minus even, that must definitely give us an even as well. So you then have an even there times by an even there, and 2 evens multiplied will give you an even number. So that's the first scenario. So in the first scenario, we get an even. So that's great. We just need to get even everywhere, and then we've proven what they are asking for at the top. Then if A and B are both odd, so let's check that scenario. So if this is an odd times an odd, then I'm definitely going to get an odd number. So all of this is going to be odd, that we know. Then if I have odd minus odd, an odd minus an odd is going to give me an even, which means an odd times an even, okay, an odd times an even number is going to give me an even. So that works out, and we get an even again. So just one more scenario to check. If A is odd and B is even, let's check. Okay, if A is odd and B is even, an odd times an even is an even. And if A is odd and B is odd, if I subtract them, I'll get an odd number. And then finally, if I times these two together, an even times an odd, that gives me an even again. So in all three scenarios, I get an even at the end, and again I get an even. So for all three cases, you have determined that your answer will be even, and you've got your answer. You have 2019 coins, 20 of which are counterfeit. A counterfeit coin differs from a genuine one only in its weight. It can be heavier or lighter, but always by exactly 1 gram. You are given a pan balance with a pointer, which shows the difference of the masses on its two pans. You are given one of the coins and asked to determine whether this coin is genuine or not, with only one weighing. How do you do this? So this is quite an interesting problem, and also very clever. But once you've got the trick, and if you can remember this trick, it is actually quite awesome. So if one of the coins need to be tested, we take that out of the total. So that one coin that we need to test if the coin is real or counterfeit is not part of the whole group anymore. So we are now only looking at 2018 coins that are left. We then take those 2018 coins and we divide it exactly in half. And we put half of the coins on the left-hand side of the scale and half of the coins on the right-hand side of the scale. Now remember, 20 of these coins overall are counterfeit. So you've got two scenarios to play out here. On the left-hand side, there might be a certain amount of counterfeit coins. Now I'm going to say there's L amount of counterfeit coins on the left, and on the right I've got R amount of counterfeits on the right. I don't know how many on each side, but I do know that if I add, so I've got two scenarios. If I add the two together, so if I take all the counterfeit coins on both sides, I should get 20. And if I get 20 for that to happen, then the coin that I'm holding in my hand, the coin that is not on the scale, then that coin is not a counterfeit coin, because I know that the sum of the counterfeits will be 20. The other scenario is if I add the amount of counterfeits on the left with the amount of counterfeits on the right, and I get 19, then the coin outside is definitely going to be the counterfeit coin, because I have to have 20.
So what we also need to understand here is that we don't know how many counterfeits we have on the left or on the right, and we are weighing
the coins. So I just want to go up to look at the scale because I took the amount of coins left, and you can see that there's the same amount of coins left and right. The ones that are not counterfeit are all going to cancel out each other's weights. So you are just, in fact, looking at the weights of your counterfeits left and right. So just going down here again, whether I'm going to add the amount of counterfeits or whether I'm going to look at the difference in the amount of counterfeits, that's more or less the same thing. You know, if you're going to end up with an even number, you're going to end up with an even number both ways, whether you add the counterfeits or whether you subtract the counterfeits. In another scenario, if we add the amount of counterfeits with their weights, just looking at their weights and not the amounts, you will also get an even. So whether you look at the amount or the weights of them, it's the same type of principle. So if the weights of the counterfeits on the left is subtracted with the weights of the counterfeits on the right, and that is an even number, you know, that means that that's the same as whether you add the weights of the counterfeits on the left with the weights of the counterfeits on the right, which also gives you an even number. So, and that's the same if you add them. So the quickest way to do this is just to check what is the weight on the left and right, subtract them, and if you get an even number, you know that that's the same as whether you add the counterfeits together, their weights, and also get an even number. And then the coin outside must be a counterfeit. Quite a clever way of doing this and solving it. Problem number 906. Let A1, A2, right up to AN be a rearrangement of 1 to 3 and all the way to n. Prove that if n is odd, okay, so in this case n is odd, that is a fact that we can see as a given, then the following expression, if I work that out, is going to give me an even result. So you can see there I am timesing quite a lot of brackets together, and I want to actually prove that this answer, after I multiply all of it out, is going to give me an even number. Now, in this case, to prove this, we are going to use what we call a contradiction. Now, to contradict something is to basically assume what you should prove, but that must be false. So in this case, I need to prove that this expression is even. So I'm going to assume that this answer is odd for my proof. And if I'm going to assume that this is odd and it doesn't work out, you know, then I know that it must be even. So I'm going to contradict the statement, if that makes sense. So you will see here that I started off by writing out the expression again, and I'm going to assume that this answer is an odd number. Now, using my parity of numbers that we've just discussed earlier, I know that if I times two odd numbers together, that I will get an odd as a result. And that's actually the only possibility that can occur, which means that all of these products here at the top, all of these purple brackets that you see here, must be odd numbers so that I can get an odd number result. Okay, so let's have a look at this. Now, how can I get an odd product? So if I look at what I have here, this 1 here is definitely an odd number. So for this first product to be an odd number, and I'm subtracting two numbers, then A1, and now you just don't get confused here, A1 is saying this can be any number and this is my first number. So it's not A1, it's not 1 as the number, it's actually any number in the world. Okay, we are just calling that A1. But 1 we know is an odd number. So for the first bracket to give us an odd, this first number, which is A1, must be an even. That's the only way for me when I subtract numbers to get an odd answer. Same for the second bracket. So we know that the number 2 is an even number. And for all of this to be odd, then A2 must be odd. So that whole process will carry on and on and on. And then we get to the last bracket, which we actually don't know, we don't know how far this pattern is going. And they are calling this last number here, they are calling that n. Now, if I just go back to the statement here, it says they prove that if n is odd, so remember we said this is a fact, we are taking that as true. So going down to the statement again, this n that we have here, they are telling us that this is an odd number. So that means that this an number at the back must be an even, so that if I subtract these two, I still get an odd number. Okay, so let's look at this again. We know that for all the numbers from 1 right down to n, so we know that this is an odd number, and we know that we are ending with an odd number. Now, if I write all of this out, this actually tells me that there must be more odd numbers in this sequence than even numbers. Now, to explain that, I just have a little small example here. I wrote all the numbers up to 7. You can see that I'm starting with an odd number and I'm ending with an odd number. And if I add the amount of odd numbers here, you can see there are 4 odd numbers, which means there must be 3 even numbers. So if you are going to start with an odd and end with an odd, your evens in between must be less. Okay, making sense. So if A1 all the way up to AN are all even, they are not going to be enough to pair up with all the numbers from 1 right up to n, because we've got odd right up to odd. And we know that AN, let's just see, AN we know is an even number. So that's going to be even. And your last is going to be even. See, this doesn't make sense, because if I'm going to go from even to even in this scenario, the even numbers are definitely going to be more than the odd numbers. But if I then pair them up with 1 to n, in this case, the odd numbers are definitely going to be more than the even numbers. So there is a big contradiction here. This whole statement is actually now falling apart, because for this statement to work, let's just go up, for this whole thing to work out and to give us an odd number, we have to have more odds than evens for them to pair up. So I can make a statement and say, thus this answer of the products can't be odd. I've just assumed that the answer is odd, but this cannot be. It is contradicting itself. So I have just proven that this product, this statement, the answer of it must be even. There's no other way.